Welcome to the presentation of the paper Texture Classification Using Features from Multi-Level Local Binary Patterns from André Bax from Federal University of São Carlos, Brazil. So, texture analysis refers to analysis of the features of an area or surface and its relation on how it reflects light, for example. It's a powerful discriminator in images, have several applications, and we have a lot of methods based on different approaches, considering that we have different texture patterns like irregular, near regular, irregular, or stochastic. Okay. The goals of texture analysis is to extract minimal information from texture patterns and images, so we can characterize visual content of an image and by evaluating the distribution of pixels, spatial arrangement, statistical properties. Texture analysis is an important research area and has a lot of applications like edge detection, pattern recognition, and a lot of tasks like segmentation, filtering, noise, or identify patterns and classify images. Local binary patterns is well-known texture analysis method, and it is based on how a pixel is related with its neighborhood. So it's a significantly discriminative feature. There's a lot of approaches that are based on LBP. Okay, so it considers a pixel and its neighborhoods to compute a decimal code. So, given as this central pixel, you analyze the surrounding pixels. If the intensity is larger than the central pixel, this pixel is assigned a value of 1. Otherwise, it's 0, so 11's higher, 1, 5 goes to 0. This is converted to a decimal code ranging from 0 to 255, and this code is used for texture classification. How? So, LBP method is applied to each pixel, texture image. This code generates a pattern. Usually, a histogram of these codes is used for texture classification. In our paper, we are proposing an hybrid approach. We are combining local binary patterns with histogram analysis, but not in the way that histograms is usually employed with LBP. LBP generates different level of pattern image from the original input image. That is what we are using. And we are using histogram to compute features from this histogram, from the patterns created by this LBP. What's the idea? First, we have that conversion from binary to decimal relies on the starting point. So we can convert that binary sequence to different decimal values based on the starting point. So we can start here, or we could start here, or here. Okay. So we have 8 different possibilities to generate an LBP map. So we have here an example. From the image, you have 2 different starting points. We generate 2 different maps, as I have different histograms of this binary code. The distribution is a little different, so these differences they are reflected in the histograms of the resulting LBP maps. We could compute a new level of LBP maps from the input texture. So we have the original image. We can compute at level 1 8 maps. From one of these maps, we could apply again LBP and compute a second level of maps, or 8 maps for each map at level 1. So at level 1 we have 8 maps, level 2 we have 64. We've considered the 2 levels and the original images, we have 73 images. Okay, we could compute features. We could go on and compute a level 3, but it will grow exponentially. We have a lot of maps that we explore in texture analysis. Let's use some simple features started from histograms from each LDP map. The idea is to use the original image, level 1, 2, and computing the histogram for each image or LDP map, and compute the best set of features, explore the best set of histogram features to discriminate the original image. To evaluate our approach, we use the 3 datasets, Brodatz, Vistex, and USPTex. So Brodatz is, we have here is a set of 40 classes, 10 images each. And the images have 200 pixel size and they are grayscale. Vistex has 54 classes, each one composed by 16 non-overlapping patches of 128 pixel size. They have color, but we discarded and use just grayscale information. USPTex is a set of 191 images. They have this size, but we crop it into non-overlapping patches of 128 pixel size. We also use them in grayscale, so it's colored color. Classification, we use LDA, a linear discriminant analysis. That's a statistical classifier based on bias-theorem, and that finds the linear combination of features that best separate the classes for samples. Results. First, we have to choose the best features to characterize the histogram that we computed from images and LDP maps. So the idea is to use simple features. So we started with mean and variance for a first evaluation. We have a lot of features that could be extracted, combined all of them. Let's get mean and variance that are traditional ones. So here we have some combinations of features using original images from level 1, the LDP maps from level 1 and from level 2. So for each we compute histogram, mean and variance, and using with a classifier. So here this ID1 experiment uses just mean and variance computed from the histogram of the original image. Here in ID6 we used mean and variances from all histograms computed for all LDP maps at level 1 and 2. They were combined in a single feature map, feature vector, and used to classify the samples. So we see that combining level 1 and 2 we can improve results. Okay, so just mean and variance from the original image achieves really poor result, and combine these features we improve the feature vector both in size and accuracy. Okay. At level 2 here we have 128 features. Here in level 1 we have 16. All original image have our success rate. Level 1 better success rate, have more features. Level 2 we improve this success rate. Now we have to add a lot of more features to improve, so the gain is not that much, but it's because we already have a high success rate. We notice that simply adding more features does not always increase success rate. We have, for example, ID6, and we improve the number of features compared to 5 to 6, but it did improve the accuracy. Okay, so features from original image are relevant for the combination. We have that LDP maps can be main or complementary descriptors. So alone they have a good result, but they complement the original features and improve the accuracy. If we add more features, for example, contrast, we can improve even more our results. So we get contrast because it's pretty different from the features that we have tested before. Just adding a new feature, we get a small increase in success rate, but we get a large increase in the number of descriptors. As here, if you remember, we have 64 images, so it's 64 more features, one for each LBP map, but we improve a little more result. If we compare with traditional and state-of-the-art methods, we see that we have a competitive performance across all datasets. We were able to surpass results on Vistex dataset, so we achieved the best results in Vistex. Okay. For the Brodatz and USPTex, we didn't get the best result, but we were close to the best methods. For example, we have a success rate of 0.75 and 2.44 lower than the best methods in that dataset. It's pretty competitive, especially if you consider that our approach is pretty simple. It's based on LBP maps that's simple to compute and histogram analysis. Work we address the classification problem of texture patterns. A traditional problem it's a classical problem in computer vision. We proposed a simple text analysis methods with simple features. We achieved good performance in all data sets. It's competitive with more recent approaches. As a future work, the idea is to explore other histogram features and investigate if additional levels of LBP maps could be used, or if you could selectively not use all LBP maps from specific levels. So level 1 has 8 maps. Do we need all of them? I could use just some of them. Some starting points are better than others. And apply the proposed methods to other image analysis problems. Thank you for watching.